So today we're going to see several things about building and training artificial neural networks. I'm going to talk a bit about this vanishing gradients problem and how rectified linear units can help solve this. This is especially important when you build deeper networks with more layers. Then we're going to see when and how to use different activation functions and the corresponding loss functions. So I'm going to explain a bit the relation between activations at the output of the neural network and the loss functions we should use. I'm going to talk a bit about some practical aspects of training the network, choosing optimizers, initializing weights, selecting the complexity of the network depending on your data, and regularization. So let's start with this problem, vanishing gradients problem. We saw last week how we can update the parameters of the network by propagating the derivatives or multiplying the derivatives of the different functions we apply, so that we can compute the derivative of the loss function, of the error that we are measuring, with respect to some particular parameter, some particular weight in somewhere in the middle of the network. To do that, we have to multiply the derivatives of all the different steps in our computation. So, for example, the derivative of the error function with respect to the output of the network, the derivative of the output of this activation function with respect to the value we put in, which is that weighted sum of all the parameters and the inputs, and so on, and chaining this all the way through the network. So if you have a very deep network, this can be a very long chain of multiplications. And the problem is that if one of these derivatives approaches zero, then as you multiply everything approaches zero, and we are left without information on how to update the parameter, because then this will be zero and the network will be stuck. So this is the vanishing gradients problem that happens when we have deeper networks. For example, if you played around a bit with the TensorFlow playground, you can see that if you build a network with a single hidden layer, for example, for this data set, you can get a good result quickly by adjusting the weights of this hidden layer. If you have a more complex data set, you cannot solve this with one hidden layer with only 8 neurons. You don't have a very good classification here. And if you add more layers, you can wait a long time and it eventually starts getting stuck and you don't have a good result. This is if you use a sigmoid activation in all of these layers. And the reason for this is this vanishing gradient problem that starts to get even more serious as you add more layers. Because with the sigmoid activation, when we deviate from the central part here, the derivatives start to approach zero. This is between 0 and 1, has these asymptotic extremities here. So as you approach minus or plus infinity, the derivatives go to 0, and then you lose information on the gradient in order to update the parameters. So this is where the rectified linear unit can help. Traditionally, so before 2012 or something like that, these were the kinds of activation functions that were used in artificial neural networks, sigmoid or this hyperbolic tangent. So basically, we have these approximations to that step function that we saw in the multi-layer perceptor, or the all or nothing response of the biological neuron, but they are approximated by these smooth functions that have a continuous derivative that we can compute. But they all have this problem of saturating, especially when the neuron is active and they saturate here and we start losing gradient information. Rectified linear unit is a lot simpler. So basically, if the weighted sum that is input into this function is less than 0, the output is 0. So here it's flat and has no gradient information, but basically this happens when the neuron is not firing. If it's greater than 0, then the output is the same as the input. So the derivative is constant at 1, and we have this line here. Now this is not a linear transformation because of this bend here. So if you take these two parts together, they are not a linear transformation, and it's enough to make the different layers non-linear, and so break that problem of having a composition of linear transformations, which is equivalent to just one linear transformation. But this solves the vanishing gradients problem. When the neurons are active, the gradient is always 1, so the gradient does not vanish. And if you compare training this network with 3 hidden layers, so here I did 1,400 and something epochs, and it still did not learn much using sigmoid activation. But if you use a rectified linear unit, even after 270 epochs, we already have a good classification here. So the propagation of the gradients there worked, and quickly the network learned enough to classify the data correctly. And you can even add more layers, and it still works fast. So this was 215 epochs, and it's quick to learn. So it makes a big difference if you're using deep networks, the kind of activation that you use in the hidden layers. So basically nowadays, variants of the rectified linear unit are the consensual activations inside the networks, with some exceptions, but they have these big advantages. Aside from being very fast to compute, because it's a very simple function, the function does not saturate when the neuron is active, so you don't lose gradient information. One disadvantage of rectified linear units is that the units can die. So basically, if the neuron is not firing for some input, there is 0 gradient information here, and the weights will not be updated. So if it happens that your neuron has a particular combination of parameters, so that it will not fire for any example in your training set, then the neuron is effectively dead, because it will not change anymore. It will always be here. Now this can be fixed with some variants. For example, leaky rectified linear units have an output, a gradient of 1 here on this side, and a small gradient here. So this is the conventional approach, divide by some constant. In TensorFlow, you multiply by some constant. So you use a small number, smaller than 1, for the leaky part here, and this prevents the neuron from dying, and it works all the same. Then there are some variants here. Parametric rectified linear units is the same as the leaky one, but instead of using a constant, this is another parameter that is learned during training. There are these randomized leaky ReLU, in which this value is drawn from a uniform distribution between 2 extremes during training, so it's always different as we train. And then when the network is trained, it is fixed at the average value between those 2 boundaries. There are some experimental results. So this is an example in comparing rectified linear units. They don't make a big difference, but typically leaky ReLU with about 5% of leak seems to work better, at least in many cases, but this is something that you can experiment. So if you're applying this in any real problem, you should try to experiment a bit. But the main message here is that do not use sigmoid activations inside the network. When you have a deep network, use some variant of rectified linear units. Otherwise, your training will get stuck, and you won't get some results. There are other more complex variants, for example, concatenating 2 rectified linear units so that we don't have a 0 here on the side. Exponential linear units have this linear output here, but then this exponential function on this part, so that it doesn't have that discontinuity in the derivative. It's a smooth derivative. This basically works the same, but it increases computational cost by having to compute that exponential, so it's not very used in practice. Okay, so what kind of activations should we use? Basically, in the hidden layers, what we need the hidden layers for is to perform nonlinear transformations so that the data gets the shape that we need for the final step. So here you just need activation so that it's not a composition of linear transformation, so the activation must be nonlinear, but it should be as fast as possible and avoid the vanishing gradients problem. So basically, variants of the rectified linear units should be used in the hidden layers in general on these networks. There are some exceptions. For example, long short-term memory recurrent networks use specific types of neurons and activations inside the architecture. We are not going to cover this, but in general, when you are designing your own network, rectified linear units should be, or leaky ReLU should be the norm for the hidden layers. The output layers are different because the output layers are what you are getting from the network to make your predictions, for example. So here, it depends on the problem that you're solving. I'm using here three examples. One would be regression. You want to approximate some continuous variable, some continuous value. So you do not want to arbitrarily constrain your output to between 0 and 1, for example, in the case of the sigmoid. So in this case, if you're doing a regression problem, the output should have no activation function. You just use the linear combination of the previous layers, and that raw value is what you're going to try to approximate to your data. For binary classification, sigmoid output is a good choice, because if you have two classes, you can interpret the output of the network as the probability of belonging to one of the classes. So something that goes from 0 to 1 is good for that, because you can interpret that as a probability. And this would be the probability of being in class 1. The probability of being in class 0 would be just 1 minus the output of the network. So if you have a binary classification problem, your network should end at a single neuron with a sigmoid output. If you have a regression problem for a single value, you should have your network terminating on a single neuron with no activation function, just the linear combination of the previous layer. Of course, you may have regression problems with with several different values. In that case, you have one neuron for each value. You can have a problem, a multi-label problem, in which you can have several different outputs that are binary. For example, imagine that you have a network to predict if the patient has some diseases based on symptoms and so on. You cannot assume that the diseases are mutually exclusive, so the person could theoretically have several diseases. In that case, you can have one output for each disease, and the output would be a sigmoid activation, and it would give you the probability of having that disease. So this would be sigmoid, also good for multi-label classification. Multi-label means that you have several outputs that you are trying to get the probability of either having or not that condition, but they are not mutually exclusive. You can have several of them at the same time. For multi-class classification, you can have, do I have it here in the slide? No. This is for multi-class classification. You can use a softmax output. The idea is that you take n neurons, the value of n neurons, you apply this formula here, where you take for each of those, you take e raised to the value for that neuron, and you divide by the sum of all the e raised to all the neurons. So basically, what this makes is a mapping between the values that you have outputting from your network, which can have several output neurons, but this maps to a vector in which all the individual values are between 0 and 1, and the sum adds up to 1. So this softmax can be interpreted as a probability distribution of belonging to one of these classes, because everything adds up to 1, and each of the values is between 0 and 1. So this is used when you have multi-class classification, which means that your examples must fall in exactly one of these multiple classes. They are all mutually exclusive, and it must be in one of them. For example, suppose that you're trying to identify handwritten digits. They must be 0, 1, 2, and so on to 9. So they must be one of those 10 different classes, and they cannot be 2 of them or 0 of them. So in that case, softmax would be the best output, and you interpret that vector as the probability of belonging to each of the classes. So we have different possible outputs for our network, and this means we must also consider different loss functions. So I'm going to quickly explain the idea of how we match the loss functions to the output of the network. Suppose that we have a set of labeled data where we have the features, the x, which is what we can usually measure, and the target values, the y, which is what we're trying to predict, that we have in the training data, but then we want our model to predict for future examples. So basically, we want to approximate some function that exists in the universe. We saw this last semester. We don't know what it is, but we want our model to approximate it. And this is a function that maps from what we can observe to what we want to predict, from this x to y. Given some training set, data, we want to find the best parameters that approximate this hypothetical function. For example, we saw that with the linear regression. We need to choose what is the best line. And in the example of linear regression, we assumed this probability model, which basically tells us that the value we're trying to predict is some function of the input plus a normally distributed error, and we want, this is the idea that we have. We have a model that approximates this f, so we can compute the probability of the data for each set of parameters that we have. So this would be our approximation with the parameters, and we can compute the probability of the data having that particular y value given the features that we can observe, the x, as being some normal distribution around our prediction with some variance. So from this, we can compute the probability of the data as a function of our parameters. Given some parameters, we estimate the probability of the data. And now we have the maximum likelihood approach, which is we're going to adjust our parameters so that the probability of the data coming up as it is be as high as possible. And this is the idea of a maximum likelihood approach. It's a likelihood, not a probability, because we are assuming that the parameters are not a random variable. They either are those parameters or something else, but they are not randomly drawn. What is random here is the sample that we got for our data. We are sampling the universe at random. We have a data set, and our data set could have been different if we had run the experiment again or something like that. So this is the idea of likelihood. We are trying to maximize what is our estimated probability of the data being as it is, assuming that those parameters are correct. And we adjust the parameters in order to do this. Okay, so for the linear regression, we have this normal distribution around our prediction. We are going to adjust the parameters to adjust the prediction. And what this ends up being equivalent to when we replace everything is this quadratic error. So basically, when we are trying to maximize the logarithm of the likelihood, and typically we use logarithms because when you are computing the likelihood, you have to multiply all the probabilities of the individual data points. And if you do this with very small numbers, then usually the computer won't be able to do that because you have an underflow on the numerical representations and lots of different problems. So if we take the logarithms, all of these end up being sums. And since we are trying to maximize some function, maximizing the logarithm will give us the same result. So typically, we look at the logarithm of the likelihood, and this ends up maximizing the logarithm of the likelihood under that assumption of the normally distributed error around our prediction is the same as minimizing the quadratic error. So minimizing the sum of the square of the differences between the predictions and the actual values. So this is why least mean squares is used in this kind of regression problems, because if you assume that the error is normally distributed and only affects the variable you're trying to predict, not the ones that you measured, then this would be the maximum likelihood solution. It's the one that maximizes the probability of the data. But note the assumptions. If you assume that the error can be in some of the x values, then it will be very different. It will not be the same thing. Once we have this loss function, then, okay, we do gradient descent and we find the smallest value, and this is what we saw previously. So this is the basic idea. We're going to find the parameters for our network that maximize the probability of the data under the assumption of that probability model that we have in our network. So depending on what the output is and how we are interpreting it, the loss functions will be different too. So in general, we have this set of data that we drew at random from the universe with some probability distribution. We don't know exactly what that is because that is the way the data is distributed in the universe. We also have a family of probability distributions in our model that depend on the parameters. So suppose you have a network that has a sigmoid output that gives you the probability of some point belonging to some class. Depending on the parameters that you have on the network, the probability distributions for your points will be different because the output of the network will be different. So we can think of the model that we have, that we are adjusting, as selecting one probability distribution from a family that depends on those parameters. Now, the maximum likelihood estimator for this theta will be the one that maximizes the probability that the model estimates the data to have using that data that we drew with some probability distribution. So this is always the same idea. We are adjusting the parameters to maximize the probability of the data. The data is the random variable because we are doing random sampling. Now, we use logarithms because of all of these products, and basically we are trying to maximize this sum of the logarithm of the probability for all the data, and this is equivalent to trying to maximize the expected probability that our model will give us, given some point drawn at random from the universe, using whatever distribution reality is giving us, and then estimating the probability of that point using our model. So we are trying to maximize what, on average, our model is going to tell us about the probability of, for example, an example with those particular characteristics having that particular class or array plane. So basically, since we are drawing this with this particular distribution from the universe, this is maximized when the distribution our model is telling us is as close as possible to the actual distribution of the data. So if our model gives us as more likely or more probable that a data point will be drawn corresponding to those data points that are actually drawn with greater probability, and vice versa for those with lower probability, this will be maximized. If our model gets this wrong, then it will be lower than it could be. So basically, what we want is that the probabilities our model assigns to the data, for example, that x corresponding to that y, will match the probabilities with which those things occur in the universe we are drawing the data from. So basically, we can measure this divergence using, for example, Kullback-Leibler divergence. This is a measure of the divergence between two probability distributions. It's not quite a distance because it's not commutative and so on, but it measures how they how apart they are, how different they are, since this probability of the data does not depend on our parameters because this is what the universe is giving us, we can change this equation to basically this product here, and this ends up being the same as the cross entropy loss. So this is the general reasoning behind this finding the loss functions for our networks, is that we want to minimize this cross entropy loss function between what our model is telling us and what the data actually is. So you will probably see in the literature a lot of references to this cross entropy, and basically the general idea of the loss functions will be to minimize the cross entropy. But of course, this part here of what the probability distributions our model is giving us will depend on what we have in the model. So this is just a general idea, but now depending exactly on the activation functions that we have at the output of the network and how we are interpreting them, this will end up being different equations, different loss functions for those cases. So let's suppose we are doing some kind of regression where we are assuming that the error is normally distributed on the variable that we're trying to predict. So we have a network, it terminates with a single neuron, we don't have activation function, and we are trying to approximate that value to our data, and we assume that there is a normally distributed error only on that prediction, not on the inputs to the network. In that case, this approach of maximum likelihood by minimizing the cross-entropy loss function will end up being the mean squared error, that one that we saw previously. So if you're doing a regression problem, you should have a linear output on your network, and you should minimize the quadratic error between the output and what you're trying to predict, because that corresponds to the maximum likelihood solution for the parameters. If you're using a sigmoid output to predict the probability of belonging to a class, I'm not going to do the derivation here, but then minimizing the cross entropy corresponds to the logistic loss. This is the maximum likelihood solution, the same as we use in logistic regression, when you are interpreting the output of your network as the probability of the point belonging to class 1. In that case, this is how you get the parameters with that maximize that probability given the distribution of your data, is to use this logistic loss function. If you are using, for example, multi-class classification with the softmax output, then you have the softmax cross entropy for this. So the idea here is not that you memorize all of these equations. This is just so that you understand that the best loss function that you use, the one that gives you the parameters that maximize the probability of the data, that is the maximum likelihood, will depend on the problem and the output of the network and how you're interpreting that output. So be careful when you're solving these different problems. Do not always use the same kind of activation function. Last week, we actually did a classification problem with least mean squares activation function. I warned you that this was a simplification, and it's actually not the most correct approach in that case. Today, you have a better idea of how this works. So today we're going to do a regression problem. You need to use mean squared error for the loss function there, and you're going to do a multi-class classification problem. So you need to look at the loss functions on the documentation and see what you will use. Okay, so once we have the loss function, we saw so far hidden layers, rectified linear units, so that things move faster. Output depends on the problem you have, the activation of the network. The loss function will also depend on the output and how we're interpreting. And now we need, once we have the loss function, we need to be able to actually adjust the parameters using the gradient information. But how are we going to do that? We have this problem of basically numerical optimization. We need to fine-tune the parameters. I'm not going to talk about this in detail, but it's useful to understand how the different optimizers function, because you can use them in carriage easily. So one of them that we saw was this stochastic gradient descent that you can get either from TensorFlow optimizers or from carriage optimizers. Actually, they are the same class, they point to the same thing, but they are in both of these modules. This one basically gets the gradient information, uses a learning rate that we provide, generally a fixed learning rate, although you can schedule some changes, and then it will update the parameters based on that gradient as we saw previously. You can include momentum, and you should, so in that case it can speed up if it's going always in the same direction. But this is basically what the SGD optimizer does. There are other approaches. Undergrad keeps a sum of the gradients in the past and then divides the learning rate by this sum. So basically, parameters that have been changing much will now get a bit slowed, and parameters that have been changing very little will now change a bit more. So it's going to adapt these steps depending on a moving average of the previous gradients. And so this can be good for convex problems where sometimes one problem is that you're zigzagging along a narrow valley, for example, and it takes a long time to reach the bottom. So if you kind of normalize the steps you're taking in different directions, you can avoid this. rmsprop does something similar, but what it keeps a moving mean of the root of the squared gradient. So it's a slight difference for undergrad. And these learning rates tend not to shrink even if you start getting to places where the gradients are smaller. This is good for non-convex problems. Usually in recurrent neural networks, this one is used. And actually, this was first used in a workshop. It was never officially published, but now it's widely used. So it's famous for being the most used unpublished optimizer. Adam mixes these things with momentum and so on. So basically, this is a more sophisticated one that joins all of these techniques to try to speed up learning, but sometimes has convergence problems. So with Adam, you can find that training is much faster, but you need to pay attention what happens at the end, because sometimes the network doesn't learn properly and goes wildly off the best configurations. So there is no real recipe for you to choose which optimizer to use, but this is something that you can experiment, try with a small sample of your data, see how things work, and try to optimize a bit the speed of training to get your results faster. However, this usually does not influence, it should not influence the quality of the final model that you have. The main impact is on how long it takes to train, to get there. Now, another thing that you need to choose is the best learning rate. So it's always useful to plot training and validation error. Last week, we only used the training loss. It's easy when you use carriage to fit to also measure validation. And the idea is that we are using part of the data and measuring the loss function on that data that we're using for training. But we're also, every epoch, taking a look at what happens on some set of data that we are not using for training. So that would be validation, and we are keeping track of how the network is behaving outside the training set. So this is an example of a convergence problem where you have oscillations on the training error. It's not unusual to have oscillations on the validation error, especially in classification, because small adjustments in the network may lead to some classes being wrong and so on the validation error. But on the training error, it should not happen, because the training error should be gradually diminishing from epoch to epoch on average over the epochs. So if you have these kind of things, this suggests that your learning rate is too high and the optimizer is jumping around the best points without hitting the points where the loss function is minimized. Another thing that can happen is that if you have a learning rate that is too small, you can take too long to learn and take many epochs. So basically, you should try, perhaps with a small sample of your data, something like that, to train for a few epochs and see if you have some problems here, reduce the learning rate a bit, and try to keep it as high as possible without getting those kinds of problems. So this way, you try to speed up training without messing things up. Another issue here that you don't have to explicitly worry in the carriage, because carriage takes care of that, but this is something you should be aware of. is how we're going to get the starting point for our network. We have in our neurons a set of weights that multiply the inputs, and then an additional parameter that is the bias that can shift everything left or right. So bias can all start at 0, it's not a problem, but the weights cannot be the same for all the neurons, because if all the neurons in one layer have the same set of weights, then all of them will receive the same updates, the same deltas for updating the weights, and they will all learn in step. They will never break apart. So this means that your layer works as if it's only one neuron, because they are all exactly the same. We need to break that symmetry, so the weights must be randomly generated at first, in order to be different in the different neurons. And the problem here is how we're going to generate these. Remember that we can have numerical problems if our values shoot to too high or too low or too close to 0, and so we need to keep those values in some reasonable ranges to prevent the network from overflowing. Especially if you're using GPU acceleration, typically we only use 32-bit precision, because that is what the GPUs use, and we need to be a bit more careful even with those ranges. So there are some initialization methods that take into account how many neurons are feeding into the neuron we're initializing. For example, this LeCun normal initializer will use a normal distribution centered on 0, and with the standard deviation that is 1 over the number of neurons that are feeding, or the number of inputs that are feeding into this neuron. So the larger the number of inputs this neuron is receiving, the closer to 0 will be the initial weights for that neuron. The Gloro uniform initialization, I think this is the standard in the default in Keras, uses both the number of neurons that come in and also the number of neurons this neuron will feed into to create a uniform distribution between these extremes. Usually you're not going to have to worry about this, but you can look at the documentation, the kind of initializers that you have. But it's important to understand that you will need this random initialization, otherwise all the neurons will behave the same and they will all learn in step, and that will not be useful. Another important thing is that the input we present to the network, and even the output in the case of regression, should be standardized, should be around 0 with a small deviation. So standardization is subtracting the average of your data, so that the average of the data is 0, and then dividing by the standard deviation, so that your data has a distribution that is centered on 0 and has a standard deviation of 1. This way, we guarantee that the magnitude of the values that go into the network is close to 1, and this is more or less the assumption on this initialization. Because note that if the magnitude of the weights was, say, 10,000 times larger, then you would need to rescale the weights accordingly in order to avoid overflow problems and so on. Another thing that this standardization gives you is a better idea of the values of the loss function. If you're dealing with different problems and you don't rescale things, the loss functions, for example, in a regression that is especially problematic, would mean different things, because if you're having a very large value, for example, you're trying to predict GDP in the tens of thousands, if you have a mean squared error of 10,000, maybe that's not too much, because the actual error is the square root of that, and so on. But if you're trying to predict something that has very small ranges, then the mean squared error would have to be something completely different. If you standardize things, you always have a general idea of where the error should be, if things are going well or not. And so, aside from the problem of learning rates and overflows and things like that, that all depend on the scale of the values that you're using, also your own intuition and the ease with which you can interpret the results can also vary much with the scale. So, standardizing the data is a good idea. Of course, if you have class labels, those are 0 or 1 or something like that, you don't standardize those. But the inputs and the output in the case of regression, you should standardize. One thing you need to remember is that you need to store those parameters, because if you are transforming your data with standardization to train the network, when you are going to use in future examples your network to make some prediction, you have to apply exactly the same rescaling. Otherwise, they will shoot outside the range. So think of standardization as changing the units of measure. You have something, for example, in meters. Now you do some subtraction and division, like going from centigrade to Fahrenheit or something like that. And then you have a new unit there. And you need to do this conversion every time you use a network. The same thing for the output in a regression. Once you get the output, if it predicts something like 0.8, but this would be the price of the apartment or something like that, you have to undo the transformation that you did so that you get the value in euros and not in your arbitrary units in which you train the net. You can do this easily in with NumPy or with Keras, but there is another thing that you can do, is that you actually can put normalizations as layers inside the network. So actually they are standardizations, but they are called batch normalization. Keras has these kind of layers. So basically you can use take the output of one layer of your network, standardize it, and then pass it on to the next layer. The way this works is by taking moving averages of the previous examples or averaging over a batch, so that when you have a significant sample passing through the network, you can normalize, standardize everything. So they call it normalization, but it's actually subtracting the mean and dividing by the standard deviation. So, and this helps training the network. But these are two different things. One is the pre-processing that you do in the data. The other is adding batch normalization layers to speed up training the network. Another thing that you need to be careful of is overfitting when you're trying to predict some new values. So the problem here is that we want to train with some data, but we want to predict outside that data. And if our model performs very well on the training set, but poorly outside, then it doesn't help us, and we need to take care of that. So one thing that we need is to measure this generalization error, so what increased error the model is doing outside the training set. And there are basically two ways of trying to minimize this. One is to select the model according to the data and the problem that we have. You can always adjust the number of layers, the number of neurons. So if you have too much overfitting, you can simplify your network. If your performance is poor even on the training set, you can increase the complexity of your network. Another way is to adjust how training is done. So this is regularization. The network is the same, but we are putting some additional changes or constraints on training, or even changing the training data that we use. We saw last semester using cross-validation to check for overfitting. This is good when you have small data sets, because cross-validation helps you take more, get more information from a small number of points. And your models are easy to train, because then you can train them several times to do cross-validation. We saw this with, for example, logistic regression, where we split the data into 5 folds. We train with 4 of them, and we validate on the other that is left out. And then we leave out different folds and keep repeating these. But note that if you have k-fold cross-validation, you need to train the model k times. This is easy to do when the model takes a few seconds to train, but if your model takes a week to train, this ends up being very expensive. So cross-validation is generally not done when in deep neural networks, because of the time it takes to train, and also because generally you only use deep learning if you have large data sets. So in that case, it's generally what we do is we leave out a sample for testing at the end. And then during training, we use the training set and the validation set, and don't do cross-validation. So to estimate the true error, you generally cannot use validation. You can use the validation set as a test set if you don't do anything with it. So you're tracking the training and validation error, and you just train one network once, and that's it. Then the validation set will be an unbiased estimate of the true error. We'll give you that estimate. But if you're using the validation error to select different networks, then you're already biasing it because you're using that information to adjust things in order to minimize that error. And that makes it biased. So generally, since we generally use validation error to try to fine-tune things, that will not be a good estimate of the true error, and for that we need a test set that we never used for any decision, and we only use at the end to get this estimate. So this is important, yes?
I don't know. I didn't follow the validation part.
Okay, so validation error, we use a training set, for example here. Or I can show the next slide.
We use it
for example, suppose that we try to solve the regression problem that you're going to solve in the tutorial, which is to predict the miles per gallon of a car, so the consumption of a car, based on the attributes of the car, the year, the power, things like that. If you use a large network with this number of neurons, 150, 10, 1 for the predicted value, you can notice that you have something like this. In the training set, you have a very small error, but in the validation set, which is outside the training set, you have a larger error. And so you decide to simplify the network to prevent this overfitting, and now you get a better network on the validation error set.
But the validation is not part of the training data.
Yes, it's not part of the training data. It's one set is used for training, for adjusting the parameters, and the other is used in parallel during training, but just to check what the error is, not to change the parameters of the network.
And we use this only for validation, and then we discard.
Yes, well, use for validation, but after the network is trained, you don't need the data. But the thing is that since you are using this validation error to decide to use this network instead of this one, because this one has a better performance outside the training set, this validation error is biased because of that decision. You already did something in order to minimize that error. So this is not an unbiased estimate of what the true error will be when you use your network in a real application in the future. So that is why, since generally we use the validation set to decide something and to optimize something about our models, we cannot use that as the estimate of the true error. It will be underestimating the true error because we did things to try to minimize it. So that's why we need to have a test set reserved for the final estimate. Okay, so remember this. In the tutorials that we're going to do, sometimes we don't do that because those are just for practice. But if you have a real problem and it's important to have this estimate of the true error, then you should reserve a test set for that, because the validation error will be used to try to optimize things. Another thing that you can find is that although you don't have a problem with overfitting, for example, in this case, training and validation are exactly the same. That's why we don't see the blue there. But they are both very high. So this means that we are underfitting. Our model cannot adjust properly to the data. So it does not make additional errors when generalizing, but it simply cannot capture the complexity of the relations in the data. So in this case, we would have a network that is too simple for this problem. Here we would have a network that is too powerful for this problem. We have overfitting. And here we would have the best network because we are minimizing the validation error. So what really matters here is the green line. It's high in this case, lower here, and high in this case too, because the green line is telling us how the model performs outside the training set, which is what matters. But when you compare the two, the red, the blue, and the green here, you can also diagnose the problem. Is it because your model is too simple, it does not capture the data correctly? Or is it because your model is too powerful and so has an overfitting problem? And these two problems can be solved in different ways. Namely, model selection, you can choose to simplify or to increase the power of the model. In addition, if you have overfitting, you can also constrain the way the model is trained, so to try to prevent that much overfitting. This is something that you cannot do when the model is underfitting. So if the model itself cannot capture the structure of the data, there is nothing you can do other than changing the model, because nothing will work there. But if the model is adjusting too much, you can try to fine-tune training to prevent it from adjusting so much. And that is the idea of regularization. So generally, the approach can be try to create a model that can work well in the training set. And then if you have overfitting, try to change the training to minimize that problem. Basically, overfitting occurs when the model adjusts too much to the specific details of the training data, and this is what's called the variance of the model. You can train the model with different data sets, and it will vary a lot between different training sets. You can try to reduce this by forcing the parameters to not run around everywhere, but try to keep them, for example, close to zero. So you can add a penalty as a function of your parameters to the loss function. This would be the loss function that you would use, for example, mean squared error or logistic loss or something like that, depending on the problem. But you also add a term here, which is a function of the parameters themselves. This can be the sum of the square of the parameters. This is called ridge regression. This is used in ridge regression, and it's L2 regularization. So basically what this makes the training do is try to keep the size of the vector formed by all the parameters as close as possible to zero. So if some parameters try to get too high, those will shrink, even if others have to be a bit larger. Another option that is often used is to penalize the sum of the absolute value of the parameters. This is L1 regularization. Basically, this is norm 1, norm 2 here. And what this does is try to force some parameters to be zero. So if there is some connections between the neurons that are not contributing much to what the network is doing, they will end up disappearing, be zero, and that will happen with this kind of regularization. So this one will try to shrink the overall size of the vector of parameters. This one will try to make some parameters be zero. L2 regularization is also called weight decay, because when you use this kind of regularization, the gradient for the loss function becomes like this, and when you go down the gradient, the update rule includes the previous value of the parameters, so it will tend to shrink the size of the parameter unless there is something to increase that size in the loss function. So this is called weight decay, because from iteration to iteration, all the parameters will tend to shrink unless they are being pulled to larger values. This penalization with L1 regularization, the gradient becomes constant there. So basically it will not shrink gradually the parameters, but it will try to bring them close to zero. If the parameter is not very necessary, it will disappear, it will be zero, and others will take its place. So these are two possible regularization methods that you can use, and you can add these layer by layer. So you can, in your network, use a mixture of these regularizations with carriage easily, and AutoDiff will compute all of this in the loss function, and carriage will take care of that. Another way of changing training is to augment the data set. This depends on the data that you're using. For example, suppose that you are using data with faces for image classification or face recognition or something like that. Since a face is still a face, even if it's slightly changed by translation, rotation, and so on, you can apply these transformations to your data, and this will effectively increase the training set that you're using. So you are changing not the model is still the same, but you are making changes to the training set to try to reduce overfitting. This is an example of regularization. But this depends on the data. For example, if you're using a network to recognize characters, you cannot do these things because if you take an A and you flip it, then it's no longer an A or a P and a B or things like that. So you cannot do arbitrary transformations for everything. It depends on what you're doing. But there are other ways. For example, noise injection. You can do this. This is on your input data, you add some random perturbations, small perturbations, so that every example is slightly different. Even if the same example comes up twice, it's not exactly the same. And Keras allows you to do this easily because you can put a noise layer anywhere you want in the network. You can also do some changes to the output because there may be errors in your labels, and if you're doing classification, instead of trying to, you can add noise there to the labels, or you can avoid 0 or 1 probabilities. So for example, in a binary classification, on your target values, you can put 10% instead of 0 and 90% instead of 1, for example, because you're not really sure of the class labels, and the network will try not to go to those extremes and be a bit more conservative in the predictions. One very used technique, this is not a particularly good example, it was just one I was experimenting with the networks, and this one came out like this. But this is just to show this plot here. You can see that on the validation error, it goes down and then it goes up again. So this sometimes happens when your network is overfitting, because you start with some random values, the error is high, you start learning and you get a lower validation error, but then you start overfitting, you start adjusting too much to the data, and the validation error increases again. So if you keep track of this and you keep scoring your models, you can go back and use the one there instead of the one that is more overfitting. So this is another form of regularization. Remember that regularization is a change in the way you're training the model, not a change in the model, in order to try to basically reduce overfitting. Underfitting you cannot solve by regularization because then no change in training will help you, but overfitting you can, and this is another example. And this one is very easy to use. As long as you track the validation error, you can do this, and Keras even allows you to do this automatically. So basically, you can put a condition for stopping that tells you if the validation error is no longer going down after some epochs, or if it starts going up or something like that, then training stops and you get an early stopping like that. Another way of solving overfitting is by averaging the output of different models. This is something that is often used. It's called bagging. For example, if you do bootstrapping on your data, you train the same model several times and you get different instances of the models because you're using different bootstrapped sets of data. And then when you're going to do a prediction, you average the output. So even though each instance is overfit to the training data that it was used, since you're averaging over several of them, you even out those errors and you get a better prediction. Doing this with artificial neural networks would be too expensive because you have very large models, they take a long time to train, and if you want to train 50 times the same neural network just to average things out, that can take the whole year just to get those results. But we can do something analogous to that, which is dropout. Dropout, during training, turns off neurons at random with some probability each time you pass a mini batch through the network. So effectively what you're doing is you are training different networks during the training of your networks, because depending on the neurons that at random are dropped out in each particular batch, you have a different architecture of the network. And as you do this many times, your whole network works like an ensemble of different networks and learns things in a way that is robust to these particular differences. So dropout works by using a probability of turning off neurons during training, and then after training, when you go to do the predictions, the neuron activations are scaled to that probability. For example, if you have a 30% probability of turning off a neuron, on average it will have 70% of its normal activation. So that's the rescaling it gets after training. All the activations of that neuron will be multiplied by 0.7 so that it's within the same range as it was on average during training. There is this inverted dropout which does the adjustment during training, and then you don't need to do the adjustment after training, but basically it's the same thing. And in carriage you don't have to worry about this because this is automatic. When you're training it works in one way, when then you do the prediction it changes the way the network is being used. So this is the idea of dropout, is to train your network as if it was a family of networks that are being randomly generated during training, and this helps reduce overfitting. So to sum up, this has been a very long lecture. We saw this vanishing gradients problem, which happened when activations saturate, derivatives drop to 0, and we lose information on how to update the parameters. We saw these activations for hidden and output layers. Basically, in hidden layers, it's always best to use rectified linear units or variants of those. But in the output layers, it depends on the problem. And this also affects the loss function that we're going to use. The idea of the loss function is always to get the maximum likelihood solution. This is always minimizing the cross entropy between the probability distributions your model is giving and the actual data. But depending on what the output is and how you are interpreting it and what you are assuming about those probabilities, it will give you different loss functions. So be careful, look up the documentation when you have a problem and don't make a mistake of using the wrong loss function. Then we saw different optimizers and this problem of trying to minimize overfitting. So there are several chapters here I've covered. This is quite a bit of subject matter, but because since this course is shorter, I'm condensing a lot of things here. I'm not going to require you to know everything in detail, but this is basically a starter for if you want to explore this field a bit more, at least you have an idea of what things you need to think about to work with this, okay? So I'm going to stop